All right, recording is rolling. Welcome to Monday, May 8th. So we're going to continue on final exam review. Now, I should say, here, let me throw this on the screen here. Right now, this is period 7, right? Which is a couple of days ahead of my other classes, right? So just for context, last week I had to proctor some exams. I wanted to make sure I got the review in for everybody for sure. So I went ahead with my last couple classes. So my 6th and 7th period are a little bit ahead of everybody else. I'm going to go ahead and post both videos. So depending on what class you're in, you can figure out which video you need to watch. Okay, all right, everybody got that? All right. So reminder on how the final exam is working. It's going to be closed notes. Although I do recommend that you take notes and have been taking notes. You guys know that I gave you guys this study guide last week. Does anybody not have a study guide? Anybody not have a study guide? Okay, so everybody's got it. Awesome, because we've been going through this for a few days, right? And so you guys take whatever notes you want. You guys know that the final exam questions are going to be the exact same as these questions, with a couple of exceptions. Some of the numbers might change, like it might say like 6 volts here, maybe it says 12 volts on the exam, right? The other difference is the packet I'm going through, the answer choices might be scrambled in a different order, right? But besides those two differences, they're all going to be the same, right? You guys remember that, right? So take some good notes, study those notes. I want you guys to understand like how to solve the problems, what the principle is behind these, right? There are a number of them that involve some short equations like Ohm's law, right? That kind of, right? But then no notes on the final exam, right? But you can use a calculator. That's fine. You guys know I have a whole class set of these, and this is plenty of computation power. Although if you have a graphing or something you want to use, that's okay too. Okay. Right. So you guys remember that? Okay. I'll remind you guys. Or actually, I think it's the first time telling you this because I just got this back on Friday. Yearbooks are available in senior dining during lunch starting today. So today through Thursday. If you pre-ordered one maybe many months ago, you can give them your name and they'll hand you a book and they'll check you off. If you haven't ordered one yet, they'll accept $105 cash only. So you have to bring cash. Well, there's probably a limited supply, so get them before they're all sold out. Okay. So you guys good with all that? All right, are we good? All right, guys ready to continue this review then? All right, so again, this is for period 7. All my classes are a little off sync, but again, gonna post different videos for different classes. All right, so where we left off back on, well, last time I saw you, I think we said to be safe in the unlikely case of a lightning strike, it's best to be inside a building frame with, and you guys said what? Steel, right? That's called a Faraday cage. Remember, that provides that electricity a path of least resistance to go through, that building, that frame, that cage, instead of you, right? See, if it was framed with wood, you might be the path of least resistance, and that would be bad for you, right? So yeah, steel. It's called a Faraday cage. We're inside a Faraday cage right now, right? All modern buildings are framed with steel, so that we're in Florida, get a lot of lightning. Right? Lightning strikes the building, not going to go through us. All right. 74. 2 charges separated by a distance of 1 meter exert a 20 Newton force on each other if the charges are pulled to 2-meter distance. So you guys see what we're doing is we're doubling the distance. Now, what is the force? Ooh, that sounds like Coulomb's law. You guys remember Coulomb's law, right? So the force of, well, it could be attraction or repulsion. Here I have attraction because they're opposite charges, right? But the magnitude of that force, right, is, we got this electrostatic constant, which is this number here. We got 2 charges multiplied together and divide by the distance squared. This reminds me a lot of universal gravitation. You guys remember gravity force was gmm over r squared, right? So the force is proportional to 1 over the distance squared. It's called an inverse square relationship, right? So guys, if you double the distance, double this distance, right? What is a factor of 2 being squared? What is that? Is that 4? And since it's 1 over that, the force is now what compared to before? 1/4. Do you guys see 1/4 of the force? Right. So 1/4 of the force. If you double the distance, you get 1/4 of the force. Now, all right. So one more thing we got to do. If the original force was 20 newtons, here, bring some paper up here. Right. If the original force was 20 newtons, and the new force is 1/4 of the old force, that's 1/4 of 20 newtons. which is how many newtons? 5 newtons, right? So that's what we're looking for. You guys can do that. Right? Everybody good? All right. 75. Electrical resistance in a wire depends on that wire's. Ooh, let me find that poster. Let me dig through here before I flash that on screen. I know I have a poster for this. I know I had you guys do a lab. You guys remember doing the Play-Doh lab? You made different cylinders, different lengths, different. Here we go. Here's what I'm looking for. Right. So what's the resistance end to end for a wire? Hey, do you think if you had a wire that was like 1 kilometer long versus 10 kilometers long, the 10-kilometer long wire would have a lot more resistance than 1 kilometer? Okay, so length matters. In fact, that's a direct proportion, right? What about a thick versus a thin wire? What do you think is easier to push electricity through, thick or thin wire? Thick, yeah. So okay, so now there's an inverse relationship, right? You guys, because the thicker the wire, the less the resistance, right? And then one more thing is this resistivity. Hey, you guys calculated the resistivity of Play-Doh. Remember, I think you guys got like 0.25 ohm meters or something kind of like that. Right? Each color is a little bit different. Okay, right. So I think all 3 of these things would matter. You guys think all 3 would matter? Let's check out the answer choices. Electrical resistance in a wire depends on that wire's, what we got here? Length, check. Thickness, check. And they have conductivity. Conductivity is just the reciprocal of resistivity, right? So check. I think all of those matter. You guys think all of those matter? Okay. 76. Compared to thin wires, the electrical resistance in thick wires, you guys just told me the answer. Thick wires, is there more or less resistance? Less. There you go. Right. If you increase that cross-sectional area, right, then you get less and less resistance. Right. Inverse relationship. The primary reason a bird can perch harmlessly on bare high voltage wires. Right. Let's see. You guys remember this? Say you got a utility pole. I got some wire. Maybe there's like 100,000 volts. I'm just gonna make up a number. 100,000 volts. Here comes a bird. Right. It's gonna get right down here. Perch 1 foot there. Perch the other foot right here. Okay. Hey guys, what is the potential difference between his feet? Like what's the difference between 100,000 volts here and 100,000 volts here? 0. So when you go over to Ohm's law, current is, well, I'll write it this way. Potential difference is really what it is, acting on resistance. Right? It's like if you connect 2 leads of a battery, the difference is like it could be 9 volts, for example. Right here, guys, there's 0 volts, 0 volts difference, 100,000 minus 100,000. And then whatever the resistance of the bird is, you still get 0 amps of current. Current is equal to 0 amps. Okay. Right, so let's go back and see what would be consistent with that. Option A, there is no potential difference across the bird's feet. Bing! That's exactly what we're looking for. Okay. Let's check the other ones real fast. The bird has large electrical resistance. Nah, not what we're looking for. The birds feet close together. Nah. Okay. So I really care about the fact that there's no potential difference. Right? There's no difference. Means that there's no incentive for the electricity to flow. Okay. If I connected the positive lead of a battery to a positive lead of a battery, okay, well, there's no difference there. When 8-volt battery is connected to a resistor, 2 amps flows through the resistor. What is that resistor's value? Ooh, this sounds like Ohm's law. Actually, I just wrote Ohm's law. Somebody tell me, what's one version of Ohm's law? Current is potential difference or voltage acting on resistance. Right. I usually write it that way, the fraction way. Here's your current. You guys remember current? Current measured in amps. Here's, I'll just call this voltage. Potential difference voltage measured in volts. And we got resistance measured in ohms, right? Right. You guys remember all that? Right. Now, what are we trying to find here? What is the resistor's value? Okay. I'm going to rearrange this. Can I say the potential difference of the voltage is equal to current times resistance? Okay. In fact, some textbooks just go ahead and write it that way. You might go to college and maybe your college professor just jumps straight to the non-fraction form. Okay, you can see that, right? I like this form because, well, let's get a step closer to what we're solving for. If we're solving for resistance, could that be voltage divided by current? Right, and they gave us the voltage, they gave us the current. So they said, I'm just reading off my paper. We got 8 volts. 8 volts acting, produces 2 amps. Right. So does that look like 4 ohms? You guys think that? 4 ohms, right? Okay. Check this again. If you put 8 volts on 4 ohms, you get 2 amps. Okay. Hey, you guys good with Ohm's law? Right? You guys could navigate Ohm's law, right? You guys wrote it down or remember it, and you'll be able to break that out on exam day. When connected to 110 volt supply, how much current is in a bulb with a resistance of 220 ohms? That sounds like a job for Ohm's law too, right? Because we got volts, we got ohms, and we're looking for a current in amps. So current is equal to potential difference on resistance, right? Actually, this is the best way to answer this particular question, because they said 110 volts, and they said 220 ohms. Like that. Oh, guys, what's that? Half an amp. Right? You could say 0.5 amps. Maybe like that way, 0.5 amps. Right? You guys get that? Right? Ohm's law. There's 2 Ohm's law in a row. Right? You guys can navigate Ohm's law? All right, everybody good? Right, number 80. A light bulb plugged into 120 volt outlet has 0.7 amps current in it. What is the power rating? And look, all the answer choices are in watts. Okay, so this is not Ohm's law. Do you guys remember what law this is? Joule's law. Power is current times voltage. There's also I squared times R or V squared divided by R. Which one are we doing? Volts. Actually, this is the version we care about. Right, power is current times voltage. Okay. We use this a lot. You guys remember like solving all those Kirchhoff tables, and you guys have used this a lot. Right? So we got 120 volts. That's right here. 120 volts produces 0.7 amps of current. 0.77 amps of current. There's your amps. There's your volts. Right. Sometimes 12 is like 84. I think this is 84. You guys think that's 84 watts? Because watts measures power, right? So you guys can break out Joule's law on exam day, heat equals IV, right? You guys see that? Right. So 84 watts, bam, right there. Okay. 81, a closed circuit is a circuit in which charge, let's see, is preventing from flowing or can flow. What is a closed circuit? Yeah, can flow, right? Here, give you guys both examples. Suppose I got battery here. I got a resistor here, right? And then, hey, the switch is turned off. There's a switch up there, right? Okay. Versus if you close that switch, now it's going to look like, well, like this bottom picture, right? So this is an open circuit up here, and this is a closed circuit here. And the closed circuit, bing, that light turns on, if that represents a light bulb. That could be a flashlight. That could be a flashlight, right? That was one of the posters, was a flashlight schematic. Close, the current can flow. As more lamps are put into a series circuit, the overall current in the circuit, more and more in series. Well, let's think about this. Okay, so get a circuit going, and I'll start adding stuff to it. Right, let's get a voltage source here. Right, well, let's call this 12 volts. Right, so got 12 volt battery, kind of like Paul Hewitt's battery is a 12 volt battery. Right? And let's throw on about 4 ohms, right? And the question had something to do with current. So let's navigate Ohm's law and see what happens. I equals V over R, right? So for just 4 ohms of resistance, that's 12 volts on 4 ohms, which is like 3 amps. You see 3 amps are going to flow, right? Right. Now let's throw a second resistor in the mix. I'll call this guy also 4 ohms. Okay, guys, what's the total resistance right now? 8 ohms. 8 ohms, right? Remember, for series, you just very simply add them up, right? So now we got the same 12 volts acting on 8 ohms. I'm looking at, what's that, 1.5 amps? Ooh, that's less current. You guys see the current just went down? Let's do one more, right? Suppose I throw in another 4 ohm resistor. Now how much total resistance? 12 ohms, so 12 ohms, right? So I get the same 12 volt battery, now acting on 12 ohms of resistance. I see 1 amp. So what's the current getting? Less and less and less. You see that? Okay, there we go. Okay. Oh, by the way, what's happening to the brightness of the bulbs as you add more and more in series? They're also getting dimmer and dimmer. Ooh, maybe another hint that that's working out that way, right? Right. Next question. As more lamps are put into a parallel circuit, what happens to the overall current? Okay, we'll switch over and think parallel. So get another track going here. All right. Let's say I got 12-volt battery again. I got 4 ohms resistance. Okay. So the current through there's going to be 3 amps. We just did that right here, right? 12 volts acting on 4 ohms is 3 amps. So you got 3 amps flowing around. Is that true? Right. Now let's connect another bulb in parallel. You guys see another 4 ohms going on right there? And hey, are there still 12-volt potential difference across this resistor? So 12 volts acting on 4 ohms. How many amps flow through this guy? Also 3 amps. The current splits. So now the battery, which was supplying only 3 amps before, is now supplying 6 amps. You guys see that? Right. Let's throw in another. Let's make this guy also 4 ohms. Check that. How many amps are flowing down this street? 3 amps again. Now the battery's supplying like 9 amps. Right? Remember, amps is like traffic flow, right? So every time you add another bulb in parallel, what's happening to the overall current supplied by the battery? It's going up, right? It's increasing, right? By the way, what happens to the brightness of each bulb as you add on more and more in parallel? Yeah, stay the same, right? As if the other ones, didn't even care about the other ones, right? Just stay the same brightness, right? All right. 85. 84. When one light bulb in a series circuit containing several bulbs burns out, right? So series, let's say this guy here, poof, burns out, right? What happens to the brightness of the other bulbs? What do you guys say? Yeah, completely turns off, right? Because we just opened the circuit. Now no electricity is flowing at all, right? There's no current at all, right? Now 85, when one bulb in a parallel circuit burns out, so let's say this guy, poof, goes away. Right? Hey, is there still current flowing through the other two? Right? In fact, it's the same current through the other two. Right? Same potential difference, right? They stay equally as bright as they were before. Right? So for parallel, I would say they burn the same as before. Okay. Right. Everybody good so far? Guys good? A short circuit occurs when, let's check these out. The positives connected directly to the negative. Hey, is that a short circuit? Positive directly to negative? Yeah, that's exactly what we're looking for. Here, let's get a battery going. Here, positive, negative. Right. If you take a wire and you connect the positive directly to the negative, right, you probably don't want to do that because if there's no resistance, right, that's a short circuit right there, isn't it? Short circuit, right? There's no resistance, right? It'll get hot really fast. It'll drain the battery really fast. Now, if you were like out camping and you had no way to start a fire, then I mean, this might start a fire for you. It may be useful in that way, but you wouldn't have. Okay. Let's check the other choices real fast. Very short wires are used. Nah, not really looking for that. Current lasts only for a short time. Okay, not quite what we're looking for either. Okay, so guys, go ahead and just choose the one that says positive connected directly to the negative. Okay, that's what we care about. Short circuit. The total resistance of 10 ohms and 7 ohms in series. Ooh, guys remember resistors in series? You can just do R1 plus R2 plus blah, 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 as long as they're in series, right? So this is series, right? So in this case, we got 10 ohms plus 7 ohms. Is that like 17 ohms, right? You guys see that? Right? In series, one after another. Right? That's like this looking setup right here. Okay, just very simply add them up. Right. 88. The total resistance of 6 ohms and 12 ohms in parallel. Ooh. Now we're doing parallel. Now, parallel, I told you a couple ways you could do this. Hold on. Let me break out my posters. Here we go. Right. You could either use the reciprocal method here. So here's what we just did. We did series. Series looks like this, and you very simply add them up. 10 plus 7 is 17. Boom, done. Right. Now, parallel, you can either say 1 over the total is, and then you can add the reciprocals, right? But what we did more often than not was just focus on 2 at a time, and we did product over sum. You guys remember that? Product over sum? But remember, you can only do that if you're doing 2 at a time. So they gave us 2. So resistance for, well, here. It'd be resistor A times resistor B over resistor A plus resistor B. Again, as long as you only have 2, right? Everybody got that? So what are our resistors? 6 and 12. So we got 6 ohms times 12 ohms over 6 ohms plus 12 ohms, right? Right, 6 and 12. Right. But pause for a moment. Pause for a moment. Right. There was a story I usually attached to this, which was a team of people get together and paint a fence. Right. Takes one guy 6 hours by himself. Takes another guy 12 hours by himself. Because if they team up, should it take them less than 6 hours to paint that fence? If you had a kind of ballpark guess, just make a guess. How many hours would it take them to paint that fence? What do you say? You guys think maybe about 4 hours? About 4 hours? That looks pretty reasonable, right? Okay. Right. Now let's just switch the story to resistors in parallel, and it's the same math. It's what we got right in front of us. 6 times 12, that's 72. 72. 6 plus 12 is like 18. 18. 36, 36, 17. Yeah, that's like 4 ohms. Yeah, look at that. It is 4. And in this case, the unit is ohms because we're talking about resistance. All right? All right, you guys good? 4 ohms. Are we good? Any question? Any question? You guys can do product over sum for a parallel, right? Of course, when you guys get your exam, I bet these numbers are going to be different, but otherwise, it's the same question. You break a bar magnet in half. Each half does. Hey, remember I gave you guys like a stack of bar magnets, and let's say I had like 4 or 5 magnets all together. It effectively acted as one giant bar magnet, right? And then you pulled them apart. Right? Now, each half was like its own little bar magnet with a north and a south, wasn't it? Right? Can a magnet have just a north and no south? Or does it always have to have a north and a south? Yeah, always a north and a south. Magnets always have 2 poles. So break a bar magnet in half. Each half becomes a bar magnet with 2 poles. Right? Right? You guys remember that? No unipolar magnets, only, I guess we call them dipole magnets. There's always a north and a south. Never just the south. Always a north and a south. A device consisting of a coil that is mechanically rotated in a stationary magnetic field. Mechanically rotated. Sounds like it could be a turbine. Could be like a water wheel. Here, I have one right here. Actually, I got 2 devices on the same poster. 2 devices. Okay? And which were they just described? They said mechanically rotate a wire in a stationary magnetic field. Is that the one on the left or the one on the right? You're right. That is the one on the left. The left. Yeah. Right. So we got a mechanical rotation. Maybe this water mechanically rotates this water wheel, which turns this coil of wires through this stationary magnetic field. That's going to transfer the energy to electric energy, right? Okay. Right. So we're talking about a generator. The answer is a generator, right? Okay. The very next question says a device that transforms electrical energy back into mechanical energy. Well, that's the right half of the same poster. Okay, so now we got. Okay.
I just did 2 AP exams.
All right, AP exam. Woo! All right, well, congratulations. You finished early, huh? All right, or maybe. All right, so nice. Congrats. Great, so we're on number 91. I'm recording this, so everybody's being recorded here. Okay. So now we got this electric energy, and it's going through this coil of wires, and it's also in a magnetic field. Hey, is that going to force this coil of wires to start rotating? That's right-hand rule. Positive force, right? We got magnetic field, we got electric current. It's going to create a force that converts electric energy back into mechanical energy, which turns the ceiling fan. That's a motor, right? There's your number 91. Device transforms electric back into mechanical. There's your motor. Okay. All right. We got that. All right. Any questions so far? Everybody do good? Number 92. Most commercial generators are driven by Steam, good call, steam, right? So not all, but most, right? So how do you get energy from coal? You boil water, that water turns to steam, turns a turbine, forces a wire past a magnet, boom, electricity. How do you get energy from natural gas? Boil water, turns to steam, same process. How do you get energy from nuclear? Boil water, turns to steam, turns a turbine, same, okay? Okay. Now, the exceptions to this might be like that water wheel I showed you, like pure hydropower, there's no steam involved. Or how about photovoltaic cells, like PV cells, solar collectors, right? These don't necessarily need steam either, right? But most electricity, right? Coal, natural gas, nuclear, good steam. Number 93, light behaves at, we're on to quantum. We're doing quantum here, right? Guys, is light a wave, a particle, or both? It is both. Has this dual nature. So remind you guys the history of this. By about the end of the 19th century, there's this famous Young's double slit experiment. Shine a light through two slits, creates an interference pattern. That's evidence it'd be wave. And so, okay, well, it must be a wave, right? That's what it is. That's the category we're going to put light in. It's a wave, right? But then 1887, Heinrich Hertz, there was that, actually got it right here. This photoelectric effect, which Einstein came along and interpreted, said, hey, if we got this direct relationship, well, beyond a certain point, between the frequency and the energy, that's evidence that light also acts like a particle. So Einstein called those particles photons. So yeah, light is both particles and waves, both wave and particle. A photocell can be activated with a blue light, but not with a red light. This is because the blue light, okay, so actually we're back to this graph. Okay? So remember, one thing scientists were trying to do was like increase the intensity of the light. So suppose it wasn't emitting any, they couldn't collect any energy, right? They turned up the intensity and it still wasn't doing anything. But beyond a certain frequency, right, now you got this direct relationship between the frequency and the energy. Okay, so where's it go with this? Oh, okay, blue light versus red light, guys. Blue light versus red light. I'm thinking between. Let's throw down these three properties: speed, frequency, and wavelength. Which one of those properties is the same for both types of light? Speed. They all travel at the speed of light, 3 times 10 to the 8 meters per second, at least through a vacuum. Okay. All right. Which one has a longer wavelength, red or blue?
Red.
Red. Which one has a higher frequency, red or blue?
Blue.
Blue. In fact, speed equals wavelength times frequency. So, yep, larger one, you have smaller the other. Yeah. So red has a longer wavelength, blue has a higher frequency. Oh, so of course you could get light possibly from blue, but not from red, right? You guys see it? I mean, it would make sense to go that way. So let's check out the choices. This is because blue light has, see, a longer wavelength, that's exactly backwards. A higher speed, they all have the same speed. A stronger electric field, a higher frequency. Blue does have a higher frequency than red light. Right? Higher frequency. The wavelength of a particle is called, wavelength of a wavelength of a particle. De Broglie. You guys remember De Broglie? It comes along and, did I hit a button? This is all looking choppy. I don't know. I think we're all right. Right. So what is the wavelength of a particle? Well, here's wavelength. Here's particle. Right. So wave-particle duality. Right. You guys remember this? Are we good? Wave-particle duality. So de Broglie wavelength. The discrete orbits of electrons are best understood by considering the electrons. Oh, that's the next poster right here. Right? So where does all this wave? Sorry, I don't know what button I hit, and these are faded out. So if you're watching the video at home, just for context, that it's looking a little choppy in class, but it's okay. We're all right. All right. So why is it that electrons can only occupy certain energy levels? They can't just be anywhere willy-nilly, like planets going around the sun. Right? How you kind of taught the atomic model, say in earlier grades, right? Right. Well, consider the wave properties of electrons, right? Electrons have such small mass that the wavelength is significant enough that, this opens up all chemistry, right? Like, why is the periodic table organized some way? Oh, well, it's because of all this. The wave property of electrons, right? Which is, here we go. the electron's wave properties. Oh, whoops, here we go. Electron's wave properties. Okay, all right. You guys good so far? Everybody going good? Right. Any questions so far? Any questions? Everybody's all good. Everybody's all good, right? Oh, get my camera reset. Sorry, I just saw my camera was knocked out of whack. I don't know how long that's been, but there we go. That's the last poster we were looking at, just in case. Okay. Here's the one before that. All right, and then I'm just showing this on the video because I just saw my camera was out of whack here. I got photoelectric effect. Okay, I think that covers this. Oh, last 4 questions right here. Nuclear fission occurs when, which, here, let me bring up my poster on, now I got a poster on this. Here it is, here it is. All right, fission versus fusion. You guys remember these right here? All right, so if you're looking at binding energy per nucleon as a function of like mass number, right? You get a curve that looks kind of like this, and it peaks at iron. Remember, Fe is iron. So if you start out with iron, it's really useless to try to get any kind of nuclear energy out of that, because that's like your worst option. Now, if you have anything heavier than iron, you can split that apart into smaller atoms, and then the difference will give you some kind of energy, right? Right? That's fission. Now, the other way you can go is if you start with anything smaller than iron. Let's say you have hydrogen, for example. You can fuse together hydrogen into helium, right? And also release a neutron and release an enormous amount of energy. In fact, like almost 1,000 times the energy you get from a fission process. Right? You guys see that? Okay, so there's your fission, there's your fusion. Right? Right, guys remember this? All right, so let's go back to, because that's these 2 questions right here, fission and fusion. So fission, is it when a nucleus divides spontaneously with no apparent reason? Okay, I don't really like that one. Is it electrical forces inside a nucleus overpower nuclear forces? Ooh, actually, I do kind of like that. Electrical forces overpower nuclear forces, because that's where we're like bombarding, for example, a U-235 atom with a neutron. We might be overriding those nuclear forces and forcing it to split, right? Let's check the other instance real fast. One nucleus bumps into another, causing a chain reaction. Okay, not quite what we're looking for. Cut nuclei with a very small cutting device. Right. Okay, when you guys see this on the exam, because there's some that are like, I don't know, maybe. Right. You guys are gonna pick electrical forces overpower nuclear forces. That's what you guys are gonna pick, right? Okay, right. Everybody know that? Good. Right. Number 98, nuclear fusion releases energy when, because now we're taking hydrogen and hydrogen, making helium, right? So uranium split, no, that's fission. Very light nuclei fused together, right? Oh yeah, of course fusion is fused together, right? Uranium, no. Heavy ions, no. Okay, so I care about very light nuclei, most prominently isotopes of hydrogen fused together. Okay. So before I move on to the next questions, just to bring you guys back into like folded society. Right now, all the operating nuclear power plants are all what type of nuclear reaction? Fission or fusion?
Fusion.
Fission. They're all fission, right? Mostly taking uranium. I think there might be some like plutonium, but these very heavy atoms and splitting them. Like here's like the most common type reaction you'll see, right? It's U-235, right? Right. Is there a lot of nuclear waste, a lot of radioactive nuclear waste that comes out of that? Yes, there is, and that's one of the issues. Is like, well, how do you like store that and deal with that and doesn't contaminate? Right, right, okay. Versus nuclear fusion, guys, is fusion a fully developed technology yet? No, we're like at the cusp. We're getting there. It's getting close, but there are no like commercial reactors that are putting energy on the grid because of this, right? But once we do, here, you guys see these 2 isotopes of hydrogen? I think it's called deuterium and tritium. Right? We've got like either an extra neutron or 2 neutrons, right? Supposedly, according to what I read on the internet, where everything is true, that the oceans are full of these 2 isotopes of hydrogen. So like once this technology is fully fleshed out, basically like all the energy that we're going to need like for like, the rest of the time this planet is even like before it's consumed by the sun, right, is available just in the ocean. So we'll just have a huge supply of energy. Okay, so that right there. Okay. Right. Oh, and is there a lot of radioactive waste from this process? No, not near as much. So yeah, so much cleaner. And again, like almost 1,000 times the energy per reaction. So that's so much better, right? Okay. 99. The primary fuel for a nuclear fusion reactor is, what did I just tell you?
Hydrogen.
Hydrogen, right? Specifically those isotopes of hydrogen, but hydrogen. And last question, number 100. A nuclear process that has relatively few radioactive byproducts is
Fusion.
fusion. If there's anything that's going to save the planet, there's a good candidate right there, fusion. All right. I think that wraps up the review unless you guys have any questions. Who has any questions about anything? Any questions about anything? All right, you guys good there? All right, so here's what we do.